So when we have symmetric data, what we want to use to describe center and spread is mean and standard deviation. So the mean, as in average, gives us an idea of center, and then a value that will be paired with that to describe spread or the variability of the data will be standard deviation. So with this, what we can do is we know how to find our mean. And what that does in terms of a number line is that tells us where we expect to land for our data. So on average, what occurs. Standard deviation is a value to summarize the spread. So a deviation is just talking about the distance a value is away from the mean. So where we have all of these data values, we can get an idea of how it deviates by looking at the difference between that value and the mean. Standard deviation is going to look at the average of those distances. So what we're looking at to calculate here is this average distance away from the mean. So the mean gives us an idea of expected value, and then standard deviation tells us on average how that value will differ. So we end up with is this number that will tell us how far above and how far below that mean we expect to go. And with that at the end, instead of just having an expected value, we kind of end up with this expected range of values that we will plan to land in if we take a random value. This is kind of a tricky concept, but once we get to a sentence answer with a little bit of context, we'll talk about this idea again because it'll make a little bit more sense. So what we're going to do here is I'm going to show you the breakdown of how standard deviation is calculated, just so that you know the formula at work, and we'll look at an example using this formula. But in the end, what we're going to use eventually is we will rely on technology to find standard deviation, because the examples we'll look at here will deal with a small sample size, but when you have larger data sets, it gets really difficult to do by hand. So I'll show you some tricks for using technology as well. But before we just rely on technology, let's break down this kind of definition and see how it applies to data and basically find the formula for standard deviation. So we have this idea of average coming through and this average distance away from the mean. So these are three key pieces that we're going to focus on. So first thing we need to do is find the mean. So what we're going to do is use this data set of 4 students, and we collected their ages 22, 19, 19, and 36. So first thing we need to do is find the mean. So what we'll do is add up those values and divide by the number of students, plug that into a calculator, and that'll be 24. Let me even put our units here, that they are 24 years old. So that takes care of knowing where our mean is. Then the next piece that we're going to focus on is this idea of distance away from the mean. So let's first talk about deviations. So deviations is this distance between each data value and the mean. So what we're going to do is take each data value, which is 22, 19, 19, and 36, and to see the distance from the mean, what we'll do is subtract the mean. So from each of those values, we'll subtract 24. And with that calculation, we'll get out a -2, -5, -5, 12. So with this, we get an idea of how far each value is from the mean. However, something that's not so good is these negative numbers, because negative versus positive doesn't have a difference in terms of distance. This is just signifying whether it's below average or above average, but in terms of distance from the mean, we don't want to have negative values coming through. So this causes an issue with our calculation. So we need to think about distances cannot be negative. So to fix that, we need to do this little extra step here to fix that. And what we're going to do is square the distances. So what we're going to do here is look at squared deviations, which will look like taking the deviation, so that x minus the mean, but then what we'll do is square each of those differences. So what I'm really going to do is take those deviations that I wrote up above there. I'm just going to write this out in long form so that you can see the breakdown of it. But then we'll take those differences and square them, which will force each of those to then be positive. So instead of a -2, we'll have a +4, 25, 25, and 144. So we do this so that we get positive values out using these squared deviations. So where we're at with this is finding this distance away from the mean for each of the values, although something we had to do to take care of those negatives is right now we're at these squared distances away from the mean. Then our next step is to average these values. And sorry, to go back, the squaring that we're doing here at the end of all of this will take care of that. We'll undo it eventually, but for now, we need these positive values, so we're going to leave them just like that. So to average these, so in averaging, we would want to add these up and divide by how many there are. So in a long form, what this would look like is I would take each of those squared deviations, add them up, and then divide by how many there are, which we have 4 data values. So that's the idea of average or mean that we talked about before. However, one little thing we need to do here, and it comes through from making up for some error that's occurring in this. We won't go too deep into this, but because of some error that we need to make up for, instead of dividing by just sample size, we actually need to divide by sample size minus 1. This idea of sample size minus 1 is called degrees of freedom. It's a very fancy way of saying n minus 1, but to make up for some error, instead of dividing by 4, we actually need to do 4 minus 1. So this is a little extra step there, but this is still the idea of average, just a little twist of using degrees of freedom instead of sample size. This calculation right here, where we're starting to get at the idea of this average distance from the mean, although this is technically average squared distance from the mean, this is called variance. And the symbol that we use for variance, if it's a sample variance, we use s squared. So s squared represents sample variance. If we had population data, the symbol that we would use is sigma squared. That would be population variance. So that symbol there, it's kind of a circle with a little tail at the top. That symbol is sigma. So we have these two forms, and it gets at the idea of this average squared distance from the mean. So what we would do is plug all of this in, and let's jump over to our calculator, and I'll show you how to plug this in the long form in a calculator. So you can separate our fraction, and then we'll plug everything in. And for exponents, there's this squared button. So you just hit that and then keep typing along. And we'll just plug in each of these values into the numerator. And this is another reason why I like the online calculator. It's because it'll separate that numerator and denominator, so you don't have to worry about layering the parentheses correctly. It'll just appear like we wrote on the paper. And then for the denominator, we have 4 minus 1, which you could type in, or you could just type in 3 if you do that in your head, but we'll have that 4 minus 1. So we're getting this variance of 66 out. So we have variance is 66. So the calculations that we're doing here, just to break it down a little bit, in the numerator, we add up the squared deviations. Squared deviations, going to shorten that a little bit, and then we divide by sample size minus 1. So if we jump ahead to the next page a little bit, I wrote down these formulas. So there's our deviation, each data value minus the mean. Then we had to go to squared deviations, which is the data value minus the mean squared. Then here's notation for variance, and I use the sample variance notation there, but there's our population variance. And what we're doing is, and it's just how I wrote it on the previous page, this is just saying, remember, this is capital sigma, so that's also called sigma, but it's the capital version. That's telling us to add, and then it's those squared deviations. So we're going to add up those squared deviations, and then the denominator, sample size minus 1, or those degrees of freedom. So that's the formula written out for variance, but sometimes it's easier to think in terms of words instead of using all those symbols there. So numerator, we add up those square deviations, divide by sample size minus 1, and this gets at the idea of average distance from the mean squared. So let's think about what happened to our units here. We started with this idea of years, and when we found the deviations, we didn't change those units at all. This is still in terms of units of years. But when we went and started squaring the value, our units also get squared. So this right here is actually in terms of years squared. And when we go and average, when you average, that doesn't change the units. This is something in terms of years squared, which is a very difficult concept. Those aren't great units to work with there. So with that, we need to make up for the fact that we squared values. We had to get rid of those negatives, but how do we undo that? So variance as a value isn't incredibly useful because when we try to put into a sentence, it just doesn't really make sense. So this is where we need to go one step further to standard deviation. And to change variance to standard deviation, all we need to do is take the square root. To make up for the fact that we have something squared here, we need the square root of it. So this is where when we move to standard deviation, the symbols will look very similar. It's just we lose the square. So lowercase s is sample standard deviation. And sigma is population standard deviation. So what we're doing is we're taking everything we did for variance up above there and just putting it under a square root. So for this data, we need the square root of 66, which we can find on our calculator here. In fact, if I just hit enter and hit square root, and then just grab the answer from above, or if you want to see it all written out, this is how standard deviation would look all written out. In the numerator, we'd be adding up those square deviations, dividing by our sample size minus 1, all under a big square root for a final answer of 8.124. And by doing that, we get our units back to where they should be. So now our units would be in years. So standard deviation, this will give us an idea of, on average, how far away from the mean do we expect to be. So in terms of that picture that I drew at the beginning here, it's that we expect a student to be 24 years old, and on average, we could expect them to be 8 years above that, so 32, and 8 years below that should be 16. So with that, it's a little more clear in terms of spread of the data, in that when we have a random student, based on this data, we'd expect them to be between 16 and 32 years old. So putting this into a sentence, and I gave a structure here that you can follow when making a sentence. So with our data, we expect the mean, and on average, that'll differ by what our standard deviation is. So what I would write for this data is with the ages of the students, we expect them to be 24 years old. And on average, this will differ by, and I'm going to round here, and for our class, in terms of the math side of it, I'll want to see the exact values, but when you go to write your sentence, you can round to what feels more natural. And maybe you want to write 8.124 years, that's wonderful. Maybe you want to round it to a whole number. I'll leave that up to you, as long as somewhere I can see the exact answer. So I'm going to round this to a whole number. So this will differ by about 8 years. So then we get this idea of center and spread. Center, we expect 24 years old, and then how it spreads is by about 8 years. So what happens on average in terms of deviation? So this is the idea of standard deviation. This was the long route, just to show you where the formula comes about. But what it breaks down to is this idea of, in the numerator, adding up those squared deviations, denominator divide by sample size minus 1, and then for standard deviation, we need a big square root over that value. Now, if we go to the calculator, what I'll show you is how to do this a little more quickly. If you're at the Desmos calculator, and I'll have a separate video for showing you how to find this with GeoGebra, but with the Desmos calculator, there's actually a really quick function. So if you see above our values here, there's main, ABC, and function, FUNC. If you click that, you'll see these different options. There's even a mean button if you need a mean real quickly, but there's a standard deviation. Now be careful, there's standard deviation and standard deviation P. The P represents population, which we do not have. So don't use that button, just use standard deviation. Then we'll start these parentheses, and all you need to do is list out the values. So if I go 22, comma, 19, comma, 19, comma, 36, done. There's the value. And with our class, in terms of your written assignment and exams, feel free to use technology to find standard deviation. I always think it's important to see where the function comes from so that you're getting this value out. If you're not sure what it represents, if you remember the formula, it's this idea of average distance away from the mean. But the important part is being able to interpret it into a sentence, linking that mean and standard deviation together. So for symmetric data, which again, when we have skewed data, we're going to use the median and interquartile range, which we'll talk about later. But for now, with symmetric data, you would describe the mean and standard deviation, and you can use this kind of sentence structure here to help make a sentence relating those two values. So let's calculate the standard deviation for this following data set. I'll show you the breakdown one more time. I'll even show you a different way of organizing your work that can maybe help. So first thing you'll always need is the mean. So we're going to add up these values and divide by our sample size, which is 5. So that'll be an 11.2. So what it comes down to is we need to average those squared deviations. So what can help is just listing out your squared deviations. So taking each data value minus the mean, which we just found was that 11.2, and squaring those differences. So there's this kind of table form of finding standard deviation that can be helpful, but the idea is, and we could go to a calculator and find each of these values individually. If you do this, just be careful of rounding too much. usually our rounding rule is to 4 decimal places. These actually come out to 2 decimal places evenly. So this would be a 67.24, 10.24, 0.64, 14.44, and 46.24. And then if we have our squared deviations, so that's getting at this numerator here that we need, we want to add up those values. So what we need to do is to combine those, add them together. And what that'll give you is the numerator for your standard deviation. So when I go to calculate my standard deviation here, this makes it a little simpler because I'll have my square root and then I'll have a fraction, and the number that comes out here will make my numerator. So if we add those up, those should add up to 138.8. So that'll make the numerator. So that's the sum of my squared deviations. And in the denominator, sample size -1. So then it's much simpler to plug into the calculator. And that should give you a standard deviation of 5.8907. So in terms of a sentence without any context here, it's that we expect 11.2 units, and on average, this deviates by 5.8907 units. So that's how we could put that into a sentence. Again, we could go to Desmos and check our answer using that standard deviation button, and then just list the data values there. And this will be nice, and like I said in another video, I'll show you GeoGebra, which will be even nicer for large data sets, to get a quick value for standard deviation, which is completely fine for our course. I won't ask you to show work in your calculations for standard deviation. Just one last little piece here. If we did add context to this, so let's say this is collecting the number of people visiting a certain cafe, meaning one day there's 3 people, one day 8 people, one day 12 people, so on and so forth. So we get a little context. Then what we could say is the cafe can expect about 11 people. I'm going to round to whole numbers here since people is usually a whole number. Can expect about 11 people. And on average, this differs by about 6 people. So then we get this idea that anywhere from 5 to 17 people, like using this 11 as a center and then 6 as this number to go above and below by, we get this range that we expect for our data. In fact, most of our data should land within that range. So when we have symmetric data, mean will give us an idea of center, and then the standard deviation will give us an idea of how it spreads out by describing this average distance from the mean.